Green button. All right. So we're going to continue our discussion of Lorentzian constraints, positivity constraints and generalizations thereof on effective field theories. And so the first toy model that we're talking about is a theory of a scalar field I called pi last time that even has a shift symmetry. Under pi goes to pi plus constant. This isn't necessary, but just so if we do this, then even the leading interaction that it can have is this one that we talked about, this constant over m to the fourth d pi to the fourth plus dot dot dot. And we saw that there was something special about the signs of k, and that the absence of superluminality implied that k should be positive. And that we saw in a number of examples. So this is a low energy effective theory. It has a bunch of higher dimension operators, many others. So this as an effective field theory can't be extrapolated to arbitrarily high energies. It breaks down somewhere in the neighborhood of the scale m, if this coupling kappa is of order 1. So it breaks down somewhere in the neighborhood of the scale m. So we can talk about UV completions of this effective theory. UV completion is nothing other than a sensible high energy theory that gives you sensible predictions in principle up to arbitrarily high scales, or at least scales much, much higher than the scale m associated with this low energy effective theory. Okay, so, and I give you a number of examples of UV completions of decent high energy physics that could give rise to low energy theories like this. We talked about a theory of pi being the Goldstone boson of a spontaneously broken U1 global symmetry, where you could generate this operator simply by integrating out the Higgs particle in the ultraviolet linear sigma model at just at tree level. We could even couple the underlying scalar to fermions and integrate out the fermions at one loop. We can talk about completely different kinds of ultraviolet physics. Pi could be the fluctuation of a brane in extra dimensions, and then the relevant effective Lagrangian. In that case, the symmetry that controls the structure of that effective Lagrangian, the symmetry that controls this structure, square root 1 minus dy squared. Just a little side comment here, but isn't it surprising that I write this formula down and it seems like it's telling me the coefficients of dy squared, this is just a kinetic term, but dy to the fourth, dy to the sixth, eighth. Normally I don't think I know the coefficient of all these higher dimension operators. Why are they all the same? Does anyone know what is it that fixes the form of this effective action if I'm talking about the fluctuations of a brane in higher dimensions? Exactly. Okay, it's the fact that it's a fluctuation of the brane that allows you to nonlinearly realize the full higher dimensional Lorentz invariance. Okay, so the brane is breaking the, let's say, the 5-dimensional Lorentz in translation, even more importantly, the translational symmetries, well, both of them. But this structure, square root 1 minus dy squared, is exactly like gamma, root 1 minus v squared, and it's that which is actually telling you that there's a Lorentz symmetry. So it's not just translations, but a Lorentz symmetry as well. Anyway, so that's why we happen to know that it has that structure. But once again, you expand this thing out, and you find that it has all positive. It has all positive coefficients. Okay, so and so then it's just an interesting question to ask. It seems like it sort of had to be that way because of this issue with superluminality, but sort of technically, why does it happen? When you actually do the loop calculation or integrate something out of tree level or whatever, why does this phenomenon happen? I'll go over here. And we decided on very simple grounds, physical grounds, that everything is controlled by the structure of this 2-to-2 scattering amplitude. All right, so let's look at this 4-point scattering amplitude. Let me just remind you of some of the basic kinematics of 2-to-2 scattering amplitudes. We're going to imagine the particles are massless. We have our usual Mandelstam variables. S is p1 plus p2 squared, and t, let's say, is p2 plus p3 squared. Okay, u is like p1 plus p3 squared, and for massless particles we have s plus t plus u equals 0. So really, we can think of the amplitudes as just a function of s and t, and just kinematically, t So S in this configuration would just be the center of mass energy squared, and T would be S over 2 times cos theta minus 1. Okay? All right. Now, another reason for talking about the scattering amplitude is that when you talk about a notion of a higher dimension operator, or actually any operators, any terms in a Lagrangian in a quantum field theory, they're intrinsically ambiguous. Okay, when you say I have, when I write down, like let's do a classic example. Let's say I even have a free theory. Okay, a free theory is a free theory is a free theory, but someone else could come along and say, no, I like another field. My field chi is your field. Let's say your phi is my chi plus some constant times chi squared. So you can do a field redefinition. And of course, the Lagrangian is no longer looks free, right? This new Lagrangian looks like d chi squared. It has some chi d chi squared, some chi squared d chi squared, all kinds of mess. Okay? So which is it? Is this a free theory, or does it have a bunch of higher dimension operators? Yes? No. So this entire business about the measure and the path integral you should just completely forget about. Okay? I mean, we can. It's extremely misleading. And there's one context where it seems useful in the Fujikawa method for anomalies. Even that's a bit of a fake. Okay? All the business about Jacobians and measure factors and determinants is just a kind of heavy-handed way of talking about a one-loop calculation. And it doesn't tell you anything about what to do beyond one loop, even in the cases where it works a little bit. Okay? In fact, but thanks for asking, because, see, this is a very good aspect of thinking in this Wilsonian terms, right? Whatever the heck you do with what you even mean by the measure, that's something that goes in the definition of what you mean by the cutoff and what's going on at the scale lambda and so on. So it just doesn't matter. Never worry about measures, okay? You will never be hurt by not worrying about measures. Precisely because no, I mean, it's not an empty statement. It's because of the first two lectures, okay? It's that whatever you mean by phi, however you're integrating over it, whatever the hell you're doing, it's absorbed into some effective action in the end, and then off you go with the rest of the lectures, okay? But just practically here, what's happening is that, of course, this is not lying to you in the sense that if you care about correlation functions of chi, you can get some complicated functions. If you care about correlation functions of phi, it'll look like a free theory. But if you care about some observable, like a scattering amplitude, then the scattering amplitudes you compute from phi and chi are identical. So this is the sort of famous fact that you can't unambiguously associate fields with particles. You can't unambiguously say, given some particle content, what field theory you're going to use to describe it, precisely because you can make field redefinitions like this. All that matters is that the field that you're talking about correctly produces the one particle states that are then going to go scatter with each other. And in fact, you can explicitly see in this theory, you have introduced some cubic interaction and some quartic interaction. And so if you compute, I invite you to do this if you've never done this calculation. If you compute the scattering amplitude in this theory, you'll find a beautiful cancellation, and the amplitudes are 0. Okay? So, but what this is telling you is if you care about some physical field redefinition invariant way of talking about something, the cleanest way of doing it is to talk about an amplitude, to talk about an on-shell amplitude, right? So therefore, even here it doesn't happen to matter because there's a very natural choice. You see, I don't want to introduce any artificial new mass scales and making field redefinitions. So this is a perfectly natural choice for writing down higher dimension operators. But the most invariant thing I could have done is to talk about a 2-to-2 scattering amplitude. So let's say, what is a 2-to-2 scattering amplitude I would get in this low energy effective theory? Well, I would get k over m to the fourth times s squared plus t squared plus u squared. And in my definition for what I mean by an amplitude for the rest of the talk, there's going to be a minus sign there. So just so we're clear once and for all what I mean by this, in order to not to pointlessly carry around some minus signs, since positivity is going to be important for me, my convention for what we're computing as an amplitude here has, for a phi cubed theory with this coupling mu, it would just be mu squared 1 over s plus 1 over t plus 1 over u. Okay, so. Okay, anyway, so this is what the low energy amplitude looks like in this theory with a minus sign, and there's some plot dot dot dot. Okay, and so what we're saying is that this amplitude at low energies looks like a polynomial, and the coefficient of the leading term has to be positive. That k has got to be positive. Yeah.
So, about the previous question, if the field redefinition involves something like box of chi,
yes.
then I think you do have to worry about the measure.
No, you don't have to worry about the measure. But everything about the measure. Oh, sorry. The question is, if the field redefinition involves boxes and so on, do you have to worry about the measure? You never have to worry about the. You never have to. First of all, everything about the measure is issues that begin at one loop. Okay. So here I'm just talking about tree level scattering. But the more general point is that whatever you do. Oh, sorry. Are you putting boxes upstairs or downstairs?
Upstairs.
Oh, no, upstairs, it's fine. The local field redefinition will just give you a new local Lagrangian.
Yeah, but you would get a body of pop-up determinant, right? And
that's just a one-loop calculation. A body of pop-up determinant is just a one-loop calculation. Sorry?
It will produce some new terms. In the case without the box, it's going to be some contact term, but when you have the box,
local things will generate local things. You'll never generate anything non-local. You can do local field redefinitions, and it'll be fully reabsorbed within some new local effective Lagrangian.
Yeah, it can be reabsorbed, but
yeah.
It's not exactly the same Lagrangian. I mean, that has an effect on your Lagrangian. I mean, when we take account of this body of power determinants for the Jacobian, it modifies your Lagrangian slightly.
Yeah, we modified it. Well, I'm saying that I'm saying going from. I'm just saying I'm saying the following thing. If you give me a theory, any two theories that differ by local field redefinition give you exactly the same physical observables, right? So this entire maybe we can bank this discussion for a little later. The point is that that when you have the kind of field redefinitions you like with boxes in them, they will involve some new dimensionful scales. Because they involve these new dimensionful scales, the entire question of how calculable this Jacobian is totally in the soup. It's in the soup of how you're regulating the theory to begin with. So it's not different than the question that we talked about. All the differences that we're discussing here, the Jacobian that you want to reliably compute, which you can't actually reliably compute without talking about what the regulator is anyway, all of those things go into the irrelevant operators, which we can absorb away into the redefinition of the relevant ones. So anyway, let's talk about it. Now, you could try to do something where you separate scales. But anyway, let's have the discussion. The more general point I wanted to make is that there's no real distinction in field theory between the part of the calculation that comes from measures and Jacobians and just doing loop calculations. So that there's nothing particularly distinguished about thinking about the integration measure. Even in cases like anomalies, where we sort of famously say there's something special about it, it's just a way of doing a one-loop calculation. All right. Okay. So let's now talk about what a UV completion of this amplitude could look like in the various theories. So let's first talk about it in that Higgs effective theory. And so let me first write down what the answer is. The answer in the Higgs effective theory, in the Higgs UV theory, this amplitude is actually s squared over s minus m Higgs squared plus t squared, or t minus m Higgs squared u squared. Times lambda over m Higgs squared. Okay, so let's see why we could have guessed this answer without doing any calculations. Okay, you know, and we're going to come back to this point over and over again, but we know that what was going on is that in the UV, I got this interaction by integrating out a Higgs at tree level. So the answer has got to have some pole when s and t and u is equal to m Higgs squared. Okay, and you see that's what's going on. It's like it's s squared of s minus m Higgs squared. But now when I go to very low energies, the s piece is gone, and so I get s squared. I get something that goes like s squared plus t squared plus u squared. But at very high energies, what does it look like? What does this amplitude look like at very high energies? The leading piece from here looks like s. So that still looks dangerous, but there's s plus t plus u. So the leading piece is 0, in fact. And so we have to go to the subleading piece that gives me a constant as you go to high energies. And in fact, what constant? Lambda, right? Because everything else, the subleading piece, everything goes away, and the constant is just lambda, which is exactly correct. In very high energies, this goldstone is united with everything else, and I just have the 4-point scattering in the ultraviolet theory. Okay, so, but from this answer, let's see why without, I mean, here we can kind of read it off, but let's see if we can understand. Let's see if we can understand why it is that that this coefficient ended up being positive. Well, first of all, so what does this amplitude actually look like in the let's say in the S plane, in the complex S plane? So I'm holding t fixed. In the complex S plane, it has a pole at s equals mh squared, and it also has a pole when u equals mh squared, and u is negative s negative t. Okay, so it has a pole out here. So it has a pole when negative s negative t equals mh squared. So when s itself is equal to negative t negative mh squared. Okay, so let's say t is slightly negative. So anyway, there's another pole here sitting at, this is when u is equal to mh squared. Okay, otherwise it's analytic everywhere, right? And in particular, in the neighborhood of the origin, it has a good series expansion. It has a good power series expansion, right? So there's a way that I can kind of more invariantly extract what I mean by, let's say, the coefficient of s squared. Okay? In fact, for just the purposes of this argument, to make life simpler, we'll come back and hold t fixed at a non-zero thing later. For the moment, let's actually send t fixed, and actually let's send it to 0. Okay, so this other pole is just at s equals negative mh squared. Okay, and in this limit, the low energy amplitude is just s squared. Okay, maybe times 2. Okay, but it's some number times s squared plus dot dot dot. All right, so how can I extract from this amplitude the s squared coefficient? Well, the s squared coefficient, this number, let's call it c. C is nothing other than it's just a contour integral ds over s cubed times m of s, maybe with a 2 pi I, but I'm not going to worry about the 2 pi i's anymore. From now on, the 2 pi i's will be in the definition of the contour integral. Okay. Oh, I just invented a new notation. Contour integral slash. Good. Okay. All right. So, okay. So that's C, right? That's how we extract C at low energies. But on the other hand, I can also see that manifestly m of s goes to a constant as s goes to infinity. So m of s over s cubed is vanishing as I go to infinity. And therefore, I can calculate this little contour integral around 0 by deforming the contour around infinity. Or if I say it another way, if I look at the contour integral around infinity of the whole thing, so if I look at integral slash m of s over s cubed around infinity, this is equal to the pole around 0. So this is equal to c plus the contribution that I get from the discontinuity across from the residue on these poles. Okay? And again, for my conventions, forever on here, I'm going to put a minus sign there. Okay? So I'm going to get the contribution from the residues around these poles. So I'm going to get the residue at s equals mh squared divided by mh squared cubed. Sorry, divided by mh squared squared. And then I'm going to get the same thing from the u side, right? And this, the answer is symmetrical in s goes to negative s, so I just get a factor of 2 from there. Okay? And so from here you see we understand what c is. So c is equal to essentially this residue at s equals mh squared. And now's the important point. What do we know about the residue without even doing the calculation, right? We know that this tree level amplitude, when you sit on this pole, it's factorizing into the product, this 4-particle amplitude is factorizing to the product of 3-particle amplitudes. That's unitarity, right? Because we know that the imaginary part of this amplitude is supposed to give us the cross-section. The imaginary part is the residue of this pole. Okay? If I put the I epsilon in, then the imaginary part of 1 over s minus m squared is delta of s minus m squared. So if I want to if I want to pick out the coefficient of that delta, it's more invariantly simply the residue of this analytic function sitting at s equals mh squared. So the residue of a tree amplitude sitting on the poles has got to be positive. Okay? It gives you the cross-section, the tree level cross-section for producing that resonance. Okay? So this thing is positive, and so that's why C is positive. So now you see we didn't say anything about superluminality, we didn't say anything about that. What are the ingredients that went into this? One is unitarity, right? So one ingredient the actual literal positivity here came from unitarity, actually, right? Which is telling us that the residue as s goes to m squared of the amplitude, the function of s is equal to something positive. We're going to go into that in more detail. The other thing that we needed for this argument is that the amplitude was sufficiently well behaved at infinity that I could close the contour. Okay? And actually, strictly what we got was we had m going to a constant. So that was way good enough. No problems, right? What could we have had? We could have had something as bad as s squared, right? So it has to be bounded by, so we also have to have some boundedness that says that m of s is less than s to the, let's say, 2 minus epsilon, okay, as s goes to infinity. And remember, this was at t equals 0. Okay, now before talking about where these things, before talking about this more, let's just see what happens in our other example, in our other simple field theory example, where we integrate out at a fermion at one loop. Now, when we integrate a fermion at one loop, the analytic structure of the amplitude is not just that it has a pole. We're going to talk about this analytic structure a little bit more, but in this case, it's familiar enough that you know what to expect. So here, what do we expect for the analytic structure of this 2 to 2 amplitude? It's not a pole anymore. You know intuitively how to think about it, right? This loop diagram is like you're exchanging a continuum of particles at tree level, right? So it should look like a sum of a whole bunch of poles, a continuum of poles. And so what you get is a branch cut instead of poles. Right? So that's the intuitive reason we get branch cuts instead of poles. The branch cuts has got to start at 4m psi squared if I integrate it out of fermion at one loop. Remember, we're talking about this kind of diagram now. So there's a branch cut that begins here. There's an analogous one on the other side. It goes in the opposite direction. But you see, the argument is now simply exactly the same. There's nothing different about it. Again, we have to observe that the amplitude goes like that the amplitude is bounded by s to the 2 minus epsilon. It most certainly is in this case, right? Once again, why are the amplitudes so well behaved in high energies in this case? Just because the high energy theory is a quantum field theory with dimensionless coupling. So the amplitudes are just given by dimensional analysis. Okay, they can go to a constant or they can even die, right? You know, in this case, anyway. There's no problem at infinity. I do exactly the same argument, exactly the same contour integral around infinity, but now I deform the contour around like this. So that big contour gives me 0, but everything else exactly the same. So one piece is this term at the origin. The other piece is now going to integrate the discontinuity across this cut. But the discontinuity across this cut is exactly the imaginary part of the amplitude. It's precisely given by unitarity as the total cross-section. In this limit, especially literally in the t goes to 0 limit, again, we're going to talk a little bit about what happens away from t equals 0 momentarily, but certainly in this simple case, the discontinuity across this cut is positive. And so we again have the same conclusion, okay, that c is positive. So now we see from a different point of view. We didn't say the word superluminality or these pictures with the turning on the coherent background and propagation and so on, but we've seen in the microscopic process, which is being concatenated over and over again when we turn on that background to enhance this microscopic effect of something that we can see macroscopically, we see that there's something in the structure of the 2 to 2 amplitude which is prohibiting this pathological behavior. And the somethings are, first of all, unitarity. So first of all, isn't this interesting? That the ultimate source of the positivity, which is guaranteeing something good about the causal structure from the low energy point of view, is a consistency of quantum mechanics in the, from the point of view of the whole theory. Okay, this is one of an enormous number of hints. I could spend hours talking about this. There's lots and lots of fascinating hints of a connection between these two ideas of causality and unitarity. You know, time and quantum mechanics are somehow tied in a more surprising way than you might naively think, sort of over and over again. This is one of many, many little examples of this sort. The ultimate source of the positivity, the greater than 0, is coming from the fact that we have to be able to give this amplitude a consistent unitary interpretation. And the other one is this boundedness. So we've got to talk about where this boundedness comes from. But this boundedness, the boundedness of the amplitude by a power of s squared at most, at fixed t, is at least one coarse but still true way that causality is imprinted into the S matrix. Right? So it's the causality and unitarity as reflected in the analytic properties of the scattering amplitude, which is guaranteeing the positivity that we need for the statement we want. Okay, so let me actually summarize what the statements are, and then I'll tell you a little bit about how we can prove them to the extent that we can. Given the time, I'll really sketch some of the arguments. If some of you are interested in seeing literally these arguments about what we know about the analytic properties of 2 to 2 amplitudes in more detail, I gave some lectures at the CERN Winter School this year, most of which were devoted to this topic. I mean, they're broadly about the same thing that I'm talking about here, but most of the lectures were about more from the ground up what we know about the analytic structure of amplitudes. So, and they're online. But I'll give you a sense. I'll give you a sense for it. Okay, so what are the statements? So first, I now want to be more precise about what unitarity is telling us. So unitarity is a more obvious one. Okay? And if you think about it, if someone hands you an S matrix and says S dagger S equals 1, then, well, you know how to, well, if someone hands you S matrix S, you can check if S dagger S equals 1. There's no imagination involved. So let me tell you what, and actually unitarity is a little bit more than this. We really talk about partial wave unitarity and the fact that the partial wave coefficients are bounded to be inside the unit circle and so on. I'm just going to give you the coarsest aspect that something is positive. So something even slightly more than this is true, but this is going to be good enough for us, and it's certainly good enough in perturbation theory to any order in any sort of weak coupling. So in other words, literally the kind of statement we need here is that, and we're always going to work at T fixed and small. So let me say a little bit more about the sort of context I'm working in. We're trying to make some statement about operators in a low energy effective theory, couplings in a low energy effective theory. So really, I want to talk about what I'm getting for these amplitudes when I integrate out whatever the massive particles are. So there's some approximation where I've just integrated out massive particles, and in that approximation, I want to get some idea of what the analytic structure of the amplitude is. So before telling you anything, let me just say something a little more general. What's the analytic structure of amplitudes in the S plane? First of all, why don't we ask much more generally, S, T, everything, you know, A, it's a little more complicated to imagine drawing these pictures in two complex dimensions. But much more importantly, B, we don't actually know. We don't know what the analytic properties of even 2-to-2 scattering amplitudes are, general S and T. Okay? And this was the reason the S matrix program failed. I mean, it was the reason for the rot at the heart of the subject. Okay, is that they thought they would be able to derive from the top down how causality was imprinted in the 2-to-2 S matrix, and in fact they couldn't do it. And let me give you one small clue as to why it would have been surprising if they could succeed to begin with. You see, in order for this program to succeed, you have to believe that the only singularities of the S matrix are the ones that are forced on you by unitarity. That's what they wanted to say, right? And for that to be the case, even though you're beginning with these amplitudes defined for real Lorentzian momenta, and then you're analytically continuing elsewhere, you have to believe that all the singularities there are of the amplitude are there in real Lorentzian momenta. Because after all, you're supposed to interpret them by unitarity. Now, on the face of it, that sounds a little unlikely. You've continued in the complex plane. Why should it be that of all the places you could have singularities, the only ones where they show up, where the branch points show up, correspond to real Lorentzian momenta? And in fact, if they were thinking, already in the simplest setting, forgetting about fancy things at loop level, non-perturbative things, just in the simplest setting, let's say you have a massless phi cube theory, and you want to calculate, some tree amplitude like this. Well, the amplitude we just wrote down is mu squared 1 over s plus 1 over t plus 1 over u, right? And here the analytic structure is just poles, not even fancy branch cuts, just poles. So is it true in this theory that you can see the poles in Minkowski space? The answer is absolutely not. You can't have S equals 0 in Minkowski space. Particles are massless, except in these very degenerate collinear limits. Right? This is the reason why in your quantum field theory courses you rarely talk about 3-particle amplitudes. Because they vanish in Minkowski space typically. In phi cube theory they don't, but for Yang-Mills theory, gravity, etc., they all vanish even in Minkowski space. And you can't access these poles in Minkowski space, even in the simplest theory. Even in at tree level in the simplest theory. There's a good reason for this. You can just ask, clearly you care about the function of of S and T, maybe even for complex S and T. But let's just stick with real S and T. Simple question. What part of real S and T space can you cover in Minkowski space? Answer, half of it. Okay? S plus T plus U is 0. So that means the sign patterns you can have for S, T, and U are 2 positive and 1 negative, or 2 negative and 1 positive. In Minkowski space, you get 2 negative and 1 positive. You don't get the other one. Okay? So you can't even get all the real invariance. Never mind funny things in the complex plane, branch points, etc. You see, the action of the singularity structure of scattering amplitudes is simply not in Minkowski space. Already at tree level. All right, and that's the main reason they ran into trouble. Eventually, you discover, even as a function of S and T, even when they're masses, even when everything seems much, much more under control, eventually you discover that there are singularities in the amplitude, for example, when T is positive. There are some new branch points, okay? And you don't have to go very far if you just calculate the first non-trivial loop diagram, the box diagram. Okay, you just stare at it and you ask, can I understand all of its branch points from particle production in Minkowski space? No. Okay. The ones that you can't understand have scary names called anomalous thresholds and even worse things. But you see, it's only scary if you expected you could do it to begin with. You shouldn't have expected you could do it to begin with for these very simple reasons. The action of scattering amplitudes is simply not. The action of the analytic structure of scattering amplitudes is simply not in Minkowski space. It's somewhere else. And you can ask, is there some signature that would allow you to see all of these poles, even at this level? And the answer is yes, it's 2, 2 signature, not 3, 1. So if you're going to do anything, and imagine it's sitting there not just in complex momenta, but real momenta and some signature would be probably 2, 2 and not 3, 1. Right? Anyway, this is just to explain why it's very hard to have an idea, a God-given idea ahead of time of what the analytic structure of scattering amplitude should be. Even what we have access to from the physical picture in Minkowski space doesn't even cover the entire kinematical space. Okay? And more importantly, when you actually look at the answer, you find that it has singularities that simply don't exist in Minkowski space. Tough. Okay, so, but why do we have any hope at all? Well, it's for the reason I said. Sorry, but let's go back here. So whatever the singularities are, I don't know it a priori, but I'm going to imagine that I've just first integrated out massive particles, and I haven't done any of the rest of the kind of running in the low energy theory yet. So I'm not including the loops of massless particles. We can talk about that later, but for the simplest beginning, I've just integrated out massive particles. So whatever the heck is going on, there's a safe zone here. Okay, there's a safe zone when S and T and other things are much smaller than the masses of the heavy particles. Maybe something's going on out here. Who knows? Maybe even up there in the complex plane. Who knows, right? But certainly, when S and T are small enough, I'm imagining that there's no singularities at all. So out here, small compared to some scale m, I'm imagining that the amplitude here, m of S and T, has a decent polynomial expansion. Okay, so we could call it some a p q s to the p t to the q. Okay, and we're interested in saying something about these coefficients. All right, now having said all of this, now we can come back to this physical point that I made last time, and where 2 hours of these lectures at CERN derive this point much more rigorously from the study of Landau equations and so on. But it's intuitively pretty clear that if you work at fixed t, if you make t fixed and very small compared to m, then in that limit, this 2 to 2 scattering amplitude is very close to a 2-point function. Right? And so for that reason, when t is fixed and small, compared to this massive scale, then we should be able to do better for what the analytic structure of the amplitude is. And there the claim is that when t is fixed and small, it doesn't have to be 0. It just has to be fixed and small compared to m squared. Then what you might hope is in fact true. Then the only singularities of the amplitude, maybe they're poles, maybe they're branch cuts, but they all correspond to physical thresholds in the S and the U channels. All right? And that's good for us because in the end, so So in other words, now in the full S-plane, it's just that t is fixed and small, but in the full S-plane, there are maybe poles and cuts and so on, but they're just sitting there on the real axis, and they're just associated with physical particle production. And that's all we're going to need, because in the end, we care about both S and t small. Okay, so we're going to do an expansion around here, but we're keeping t small to begin with, and we're going to use the knowledge about what S is going on, about S far away, to use these dispersive arguments to determine something about these coefficients. Okay, so now what I have to tell you, now that we've decided this is what the analytic structure looks like, now what is it that we need to know? We need to know something about the discontinuity across these cuts, and we need to know something about the boundedness at infinity. And so those are the two things that we're going to get from physics. So unitarity is going to tell us is going to give us a formula for the discontinuity of the amplitude as S is at any fixed m squared, as S goes to some m squared in t. I'm going to get a formula for this. And causality is going to tell us that m of S and t, again fixed t, always is bounded by S to the 2 minus epsilon as S goes to infinity. Yes?
Just about the answer. You assume that there is this mass scale M,
Yes.
and T is much smaller than
Yes.
scale. But what did you assume about S? S could be
S could be anything. S could be arbitrarily large. Yes, right. That is the point. The point is that just when t is fixed and small, then the 2 to 2 scattering is like the propagation of one fast particle in the background of some. It's like far away scattering, right? Propagation of one fast particle in a background set up by the other. Okay? And that's why effectively it turns into a 2-point function. In fact, anyway, you can do quite a bit better than that, and that's what. But this is a very good intuitive reason why it's true. Just so you know what these words mean, how can we say anything more than these words? Well, you have to have some idea where the branch points of amplitudes are. And then what you can do, and this is restricted in a sense to staring at perturbation theory, but to all orders in perturbation theory, and then hoping that what you learn from that is portable in general. Okay? But Landau gave a general characterization. It's very coarse characterization, very, very coarse characterization, but still a decent general characterization of where you can expect branch points of scattering amplitudes to be from the study of completely general Feynman diagrams. So they reduce to the solution you draw any old graph, and you have to solve a bunch of equations that correspond to putting to propagators to zero in the graph and associating Schwinger times with all of the or Feynman parameters with all the edges of the graph. And so the ability to solve these Landau equations puts constraints on the external data that tell you where the branch points can be. Okay, so fortunately, it sounds like a potentially impossible problem because you have arbitrarily big graphs. But in fact, the study of these graphs is very similar, and the equations have a close correspondence to the study of electrical networks, where it's known that there are simple reduction moves that you can do on the networks to reduce them to simpler problems. And in various cases like this one, for example, when t is fixed, you can actually prove that there are no other solutions of the Landau equations other than this one. Okay? But then you can also see that there are other ones corresponding to these anomalous thresholds and other scary things. Much worse things than that can happen as well. When you make t big and positive. All right? Okay, but I think you get enough of an intuition for why in this limit we should be able to say something. Okay, so let me tell you what these two statements are in more. Let me tell you what we know about the. Put a little more flesh on those bones. So first. There's a formula for this discontinuity, so let me tell you what the discontinuity is. We use the fact that when t equals 0, that discontinuity was the total cross-section. It had to be positive. But more generally, this is what the unitarity is telling us is that the discontinuity of m at anywhere in S, I'm just calling it at S as S equals m squared, and T has to be represented as a sum over spins. It has a partial wave expansion. A sum over spins, PS, and Lejeune polynomials of cosine theta. In d spatial dimensions, these are called Gegenbauer polynomials. I'll tell you how to think about them in a moment. Of cosine theta, which is 1 plus 2t over m squared from the formula that I gave you. Okay, so the discontinuity at s equals m squared, you should think of this formula as telling you that you can interpret the discontinuity at s equals m squared, whether or not something was happening at tree level, 1 loop, 100 loops, as I'm producing a bunch of particles with positive probability of spin s. I'm producing a spin 0 particle with probability p0, spin 1 with probability p1, and so on. Now, if it happens to be tree level, I'm just going to make a few particles. Already at 1 loop, or more generally, I have a whole continuum of spins. So I'm going to have an infinite tower of spins coming out of this. But if you're an experimentalist, no one told you anything. You would just sit there, you'd measure the cross-section, or you'd do a partial wave expansion for the amplitude, and you'd say, yep, I'm producing all these particles with higher and higher spin. And it's a theorist who comes along and says, oh, you know what is it you're actually doing? What you thought was that spin 1,000,000 particle was actually 2 particles you produced at 1 loop with relative angular momentum 1,000,000. Okay? So that's all this formula is saying. Okay, so let's talk about what these guys are. And the simplest way of thinking about it is to actually imagine I was doing this calculation at tree level. Okay, so let's say I have a spin 0 particle and a particle of spin s, so mu1 through mu s. And let's work out what this 3-particle amplitude is. Okay, so this guy has mass m and general spin s. I have some massless scalars on the outside here. And we don't actually have to write down a Lagrangian or think to write down the answer for what this 3-particle amplitude is, because what could it be? This guy has a polarization vector, epsilon mu1 through mu s, right? The polarization vector has to satisfy that it's transverse to the momentum and also that it's traceless. Okay, but that's it. And so let's just try to write down anything we can for the 3-particle amplitude. You'll see this more from Mark Spradlin's talks for the massless case, I'm sure. But already we can solve this problem totally. So imagine it was spin 1, for example. So spin 1, what can I write down? I have to write down epsilon mu. It has to contract with something. So it has to be A P1 plus B P2 plus C P3. And P3 contracts to 0. P1 plus P2 is negative P3, so that contracts to 0. So the only thing it could be is P1 minus P2. Right? So all I can have is epsilon mu times P1 minus P2 mu with some coupling constant. We don't have to think or write down a Lagrangian or do anything else. Okay, so what is it in general here then? In general, this 3-particle amplitude is just epsilon mu1 through mu s, p1 minus p2 mu1 through p1 minus p2 mu s with some coupling constant g. So now suppose you produced this particle. You're exchanging this particle at tree level. What is the residue sitting on the pole when s equals m squared? Okay, so if I'm exchanging this thing at tree level, the residue as s goes to m squared is just g squared. Again, that's the ultimate origin of the positivity. We're just squaring a coupling constant. but I'm going to have a sum over all the polarizations of the particle, epsilon mu1 through mu s on one side, and epsilon nu1 nu s on the other side. And then on this side, I'm contracting with P1 minus P2, mu1 through mu s. And on the other side, P3 minus P4, nu1 nu s. OK? Now, let's actually try to do this calculation. After all, what do I get when I sum these epsilon lambda lambdas? I mean, without thinking too much. I'm just going to get a bunch of etas, right? Eta, eta. I'll get eta this, eta that. I might also get eta this, eta that. Okay, so I can, in principle, get just a lot of etas. All right, let's think a little. Let's make our life a little simpler by going to the center of mass frame. If I go to the center of mass frame, in the center of mass frame, this epsilon 4 vector has all vanishing time components for this massive particle, right? So all of those contractions just end up involving the spatial components. So let's just focus on what that epsilon part is. So it's going to be some tensor. I don't know what it is, what I get from summing over all the polarizations, but it's some tensor Ti1 through Is, J1 through Js. And on one side, it'll contract into the P1 minus P2s that I'm going to call X. And on the other side, into the P3 minus P4s that I'm calling Y. So X here is the spatial P1 minus P2. Y is the spatial P3 minus P4. Right? And T is some tensor, which is just a bunch of now delta deltas, right? Just a bunch of deltas that are contracting the indices together. Now, the only hard part of this problem is, for example, for spin 1, there's nothing to do. It's just delta. It's just, there's nothing to do. It's just Tij. It's just delta Ij. Done. What about for spin 2? Now for spin 2, there's two kinds of things, right? Where you have the delta delta where they go across, and some deltas where they contract between themselves. And they both have to be there. Why do they both have to be there? Because this had to be traceless. The fact that the epsilons were traceless when you trace any of their own indices means that this tensor has got to be traceless if you take out the traces either on the I side or on the J side. So that's all you have to do. If you have patience to sit down, for example, for spin 2, just do it by hand. You don't have to do anything fancy. Just write them all down like you normally do when you take out traces, put coefficients, take the trace, set it to 0, you determine the coefficients. But you see, starting with spin 2, this tensor will depend on the number of spatial dimensions you're in, whereas it doesn't for spin 1. Okay? So, but there's a nice way of dealing with all this combinatorics in one go. Okay? And this is exactly what Lejeune polynomials are about. And Gegenbauer polynomials in d dimensions are simply about taking care of taking out the traces in a convenient way. So what is a convenient way of doing it? Well, let's just think of this guy. Let's just think of this as a function of x and y. And what is the traceless condition? So if I call this function f for a second, what is tracelessness? Tracelessness is a very pretty condition that if I take the Laplacian of this in x, let's say, I get 0. Or in y. Right? Just take two derivatives, ddxi, ddxj, just pulls out two coefficients, and I contract them. So tracelessness says that the Laplacian of this thing is 0. And that immediately gives you a clue for how to write all of these guys down at once. Let's say I want to make a generating function for all of these guys at once. So I want to make some function where I sum, so I pick out in different coefficients this with more and more x's and y's. All I have to do is write down a solution to Laplacian of something equals 0. And we know how to do that. Okay, so in d spatial dimensions, clearly I can take Laplacian of 1 over x minus y to the power of d minus 2 is equal to 0. Let's say I take the Laplacian in x of this is equal to 0. Okay? But that means that it's guaranteed that if I expand this thing around x equals 0 for fixed y, but I expand it around x equals 0, it's guaranteed to give me a series whose coefficients are those guys. Right? So if we call this sucker, if we call this guy, by definition, just taking out the overall x to the s, magnitude x to the s, y to the s, some g of cosine of x dot y over xy, which is cosine theta. So this is just defined to be what I'm interested in. These are these Gegenbauer polynomials. Then we now have a generating function for these Gegenbauer polynomials, which is just conveniently, if I normalize y to have unit norm, it's 1 over square root of 1 minus 2y minus 2r cos theta plus r squared is equal to the sum over spins r to the s gs d spatial dimensions of cosine theta. Okay, so this is a generating function, to the d minus 2. Right? So that's everything you need to know about Gegenbauer polynomials. So we can just expand this out for any d and just get the answer. So for example, for spin 0, the Gegenbauer polynomials are 1. For spin 1, the Gegenbauer polynomials are cosine theta in any number of dimensions. And as I said, starting at spin 2, it depends on the number of spatial dimensions. There's an overall normalization that's convention dependent, but the way I like to normalize it, there's a cos squared theta, which you'd expect for spin 2, but there's a normalization minus 1 over d, which is taking out the traces. Okay? The minus 1 over d is taking out the traces. But doing it like this, you don't have to manually take out traces. Okay? We've taken out all the traces once and for all. Okay, so that's what we see at tree level then. We see that at tree level, the discontinuity of the residue of the amplitude as s goes to m squared has to be a sum over Gegenbauer polynomials with positive coefficients. And at loop level, it's exactly the same thing. It's just that we can think of the thing that I'm producing at loop level as this whole tower of higher and higher spin effective particles, where the effective particle is just the composite of whatever it is that I was making. Because all that matters is its spin. You see, that's part of the beauty of the fact that the 3-particle amplitude is completely fixed by symmetries, the structure. There's nothing else that it can depend on other than just what we wrote down. This is just again, it's just the partial wave expansion said from the particle physicist's point of view of gluing together 3-particle amplitudes. All right, so let's summarize again. We learned that unitarity tells us, so now we have understood this formula, okay? Where these p's are positive. Now let's talk about causality. And I've said already that causality has to do something with this assumption of the boundedness of the amplitude. Actually, causality has to do even more fundamentally with the fact that the amplitudes are analytic at all. Okay? That they have some analytic continuation to the complex plane at all to begin with. That's the most important thing. And then on top of that, you learn something about boundedness. And as I said, I can't sit here and give you a first principle derivation because none exists. Okay? All we have done, all anyone has done in these 60 years since thinking about this problem is begin with the case of the 2-point function where everything is under control, and then make guesses and study things in perturbation theory and try to learn what the actual rules are. But let's at least quickly review what the story is for a 2-point function, because that at least gives us the inspiration for what we're looking for. So causality in 2-point functions. So let's say you have some disturbance in the time domain. You know, you're turning on something. You want to see a Green's function response to being kicked. Okay? So there's some causal Green's function, g of t, in the time domain, right? And its causality is simply that this is equal to, this is something for t bigger than 0, but is equal to 0 for t less than 0. Okay, so in physical space, causality is a statement about something sharp, right? That the response must happen after the signal. Okay, so now we can ask, so this is in position space. We can ask what this implies in the frequency domain. So what does this imply for the Fourier transform? How am I doing for time? Oh, not well, but okay, it's okay. 13 minutes. Okay. Okay, well, let's look at what it implies in the time domain. So let's look at the Fourier transform in energy space, which is integral dt, in principle minus infinity to infinity dt, g of t, e to the I et. But precisely because g of t is causal, it vanishes when t is less than when t is less than 0. So this integral can be replaced to go from 0 to infinity. And now that it can be replaced to go from 0 to infinity, you see, first of all, it's analytic in the upper half plane of E. Okay, if I give E a positive imaginary part, I'm just making it converge even more. Okay, so the first thing we learn is that we get analyticity. So this is the connection between analyticity. And secondly, we see that it's bounded by polynomial at high energies as well, right? So off in the complex plane, second I give E even a tiny imaginary part, there's an exponential, which is killing everything. Okay? And so this is bounded by e to the n, by some polynomially bounded in n. It can't beat an exponential as you go to infinity. Okay? So these are two simple consequences of causality. Now let's go backwards. This already has some interesting sort of qualitative consequences that tells you a lot about why, for example, quantum gravity is hard. Why is it hard to UV complete things? Why can't you just do stupid things to UV complete? So let's imagine you're going the other way. Let's imagine someone gave you some Green's function in the time domain. Like, say, g of e equals 1 over e squared, like a propagator, or maybe 1 over e squared minus k squared. Okay, but we're just thinking about the dependence in time. So anyway, we just care about the dependence on e. See, this satisfies all the rules, right? That just has poles on the real axis. And if I put for the causal propagator, if I put the I epsilon in the correct place, it's free of singularities in the upper half plane. Maybe I've moved the pole into the lower half plane. Okay, good. So the causal Green's function satisfies the rule, as it must. But now let's say, now put on your quantum field theorist hat and say, I know when I do loop integrals with propagators like this, I get divergences, ultraviolet divergences. So I have a brilliant idea. I'm going to modify the theory so that the propagator at very high energies is exponentially damped. There, I'm a genius. Okay? Yes?
While you define the Fourier transforms, are you assuming that you can close the contour at infinity?
No, I'm not. For going backwards, we're going to be assuming that. Here, this is the definition of the Fourier transform, and it patently gives you an analytic function of E. Okay? Now, when we want to go the other way, when I give you g of E, and I want to go back to g of t, then I might have to assume something about being able to close the contour, which is the equivalent thing. That's just about what I'm saying now. Okay? So, but just to say, if you did this and you shove this in loop diagrams, you're done. The theory is finite. Everything is great. So what's all this fuss? What's all this fuss about string theory, hard to UV complete things, and so on? Why don't we just do this? By the way, if you go to Euclidean space, there are plus signs everywhere here. Okay? No problem. This is completely fine. This is like some kind of lattice, some kind of softening form factor in Euclidean space. No difficulty with this at all. But when energy is thought of as a real energy in real time, what's wrong with this? It tremendously violates this rule, right? This is not polynomially bounded in E. Okay? And that's the problem, you see. You can smear things in Euclidean space, no problem. and there's like hundreds of crappy papers in the literature about this subject that you should ignore, okay, you can smear things in Euclidean space, no problem. The difficulty is when you smear things in Euclidean space and you try to continue back, they'll be smeared in Minkowski space. Smearing in Minkowski space is not so good, because smearing means that you could smear forward in time and backward in time. There's absolutely nothing that guarantees that you'll only smear forward in time. Okay? In fact, you don't. Right? So that's why we can't just trivially UV complete things by making guesses to exponentially shut things off at very large momenta. Okay. So that's for two-point functions, and we take that as inspiration. There's more than inspiration, of course, but all I have time for now is inspiration that causality is somehow reflected both in the analytic structure of the scattering amplitude and its boundedness. So far, we've only seen that it's just bounded by some polynomial. We've seen in our examples we need more. We need it to be bounded by like s squared or something like that to be useful. So for this, we need a little bit more. And here again, there's a more rigorous argument. The words around this are the Froissart bound. But let me give you the intuitive argument. The intuitive argument is since we're, in everything we're doing, we're imagining that t is fixed and small. T in fixed and small is like the Eikonal limit. Right? T is, we're talking about very small momentum transfer. And so it's useful to use, this is not an approximation, it's a representation. It's an Eikonal representation of the scattering amplitude. So if I imagine I put t equals some negative momentum transfer squared in the direction transverse to the particles coming in. So here are the particles coming in. I'm in the forward limit. So this is the transverse direction. So this is the momentum transfer q perp in the transverse direction. Then this amplitude is given by negative 2is, it's a little conventional, an integral over the impact parameter, here written in 4 dimensions, e to the I q dot b. And there's a phase here, e to the 2i. This is the scattering phase that depends on the impact parameter. Okay. Now, for example, in Born approximation, delta would just be the scattering amplitude itself, or the Fourier transform of the scattering amplitude, if I just expanded this out. So just to have some idea, we expect that delta should be polynomially bounded in S for the kind of reasons that we're talking about. So we expect that delta should be polynomially bounded in S. Oh, sorry. Also, we expect, since I've only just integrated out all the massive particles here, I also expect that, what am I doing? There's some kind of effective range of the interaction of order 1 over m. And so I expect that when the impact parameter b is much larger than 1 over m, that delta is just dying. I have to have the Yukawa suppression from the massive particle that I have to exchange at longer and longer distances. So in fact, I expect that delta should go like e to the minus mb, and maybe s to a power. Now that's enough to tell me that b itself is sort of something of order 1 over m. That's what you'd naively expect anyway. At worst, having this power of s means that there could be a log here. And therefore, if I go back to this formula for the amplitude in this limit, this integral is dominated by b's up to around 1 over m log s. And so from here, I conclude that m is bounded by s over m log squared s. Okay, just b itself is of order, over m squared with some constant. Okay, but the important point is bounded by s log squared s. Okay? the s out in front of the whole thing just have to be there by dimensional analysis to eat up the powers of b. Okay, so now here I assume that we have a gap. I mean, I've only integrated out massive particles. I haven't done anything else. I don't have too much time to talk about it. But in fact, it does not matter so much, right? The fixed momentum transfer t itself is giving you some kind of some effective possible size of the range over which the scattering is taking place. And so even if you have massless particles, there's a similar formula. Instead of m downstairs, you can get t downstairs. But now you know more about the particles that you're exchanging. And so in particular, you could be exchanging a graviton, okay, up to a graviton. So when you have massless particles, there's a similar formula that should be true, except you can get an s squared up here over t. And when you look in a little bit more detail, you can convince yourself that you actually always have to go down a little smaller than s squared. Okay? So you see, in practice, they're not very different from each other. Standard Poisson bound tells you the amplitude can get as big as s to the 1 plus epsilon, but it's smaller than s squared. And even when you have up to graviton exchange, it tells you that it can't hit s squared. It's s squared or a little bit smaller. In both cases, even this biggest power of 2 is compatible with dividing by s cubed for what we needed to do for closing our contour arguments. Okay? But anyway, this would take a little longer to explain where this comes from. This is the sort of more famous old result. Okay, so we have seen then these two statements, right? That unitarity tells us the discontinuity of the amplitude is is positively representable as a sum over Gegenbauer polynomials, and causality is first most zeroth order telling us the amplitude is analytic to begin with, but it also tells us something about the boundedness of the amplitude at large s when t is fixed. Notice we know very little about the boundedness of the amplitude at large s and t, let's say. Like at high energy fixed angle scattering. For example, in string theory, that amplitude is exponentially small in the physical regime, and it's exponentially large in the unphysical regime. So we know very little about what's a priori, what's meant to happen there in general. Now, I have like 7 minutes or something, right? Even less?
Where 7 is 1.
Where 7 is 1. All right, excellent. It's hard to fool you like that, huh? All right, so let me just, since we've done all of this, I just want to just quickly show you that this stuff has real teeth. So let's check that string theory satisfies these rules. So here's an amplitude for colored scalar scattering in string theory. Okay, I'm just giving you one simple example. We could do gravitons. I just want to do something where I don't have to write down any polarization vectors or anything. So imagine I had 10-dimensional gluons in some open superstring theory. I compactify to 4 dimensions. I have a bunch of scalars. I'm just scattering those colored scalars, so I don't see any polarization vectors. Okay. So the amplitude is s squared, and this is a Veneziano-like amplitude. Right? That's a tree-level scattergram. It only has poles, so we're in great shape. Right? We know what we're supposed to check. We have to check that it's unitary, which means that sitting on the residue of the poles, we have to have an expansion in terms of Gegenbauer polynomials with positive coefficients. And we have to check that if t is fixed and s goes to infinity, it's bounded by s squared. Okay, so let's check the first thing, the second thing first. It's very easy. What happens as t is fixed and s goes to infinity? Let's start with t is 0 and s goes to infinity. What does this thing look like? There's an s squared from here, but there's a gamma of negative s over gamma of 1 minus s here, so there's an extra s downstairs. And so as t goes to 0, this goes to s. Great. Perfectly good, right? If you turn on a little t, it's s to the 1 minus something, right? It's s to the 1 plus t, but t is negative in the physical region, so it goes down, right? So good, it satisfies causality. Notice that if I wanted to, take some, like here's a gravitational amplitude. I'm just repeating something I said before. That's what a graviton amplitude looks like, for example, g Newton s squared over t. And here's a dumb UV completion of it. So why isn't this the theory of the world and we're done? Because it violates the causality bound, right? So that's why we can't do these idiot UV completions just by making guesses for the amplitudes where they become exponentially soft. And that's not what string theory does. Okay, so it's not exponentially soft everywhere. Okay, when in the Reggie limit where t is fixed, in fact, goes like a power. Okay, now what about unitarity? Unitarity is the real magic. So I'm just going to do this check and write down a formula, and then I'm done. So unitarity, let's look at the pole. First, I could have poles as s goes to 0. That one happens to not be there because it's killed by this s squared out front. Yeah. Then there's a pole at s goes to 1. So what is the pole at s equals 1? The residue of this pole at s equals 1 is just 1. Let's forget this s squared out in front. Okay, I put s equals 1, so this gamma cancels gamma. The residue is 1. So here the residue is 0. Here the residue is 1. As s goes to 2, it's more interesting. The residue is 1 plus t from the gamma over gamma. And when the s goes to 3, the residue is 1 plus t, 2 plus t. Okay, and it keeps on going from there. We just get more and more products of these guys. Okay. Now, does this satisfy unitarity? Well, that's fine. That's just a spin 0 particle. So we learned we've exchanged a spin 0 particle. That's fine. You learned you exchanged a spin 1 particle. But let's look at this one. This one is interesting. See, I have to see that 1 plus t, 2 plus t, can I express it as a sum over Gegenbauer polynomials with positive coefficients? Now remember, t is equal to s half cos theta minus 1, which here s is 3, so this is 3 halves times cos theta minus 1. And therefore, 1 plus t times 2 plus t is 3 halves cos theta minus a half times 3 halves cos theta plus a half, which is which is 9/4 cos squared theta minus a quarter. Let me write this as 9/4 cos squared theta minus 1 over 9. Okay, now, this guy has to be expressible as a sum over Gegenbauer polynomials with positive coefficients. Now, the cos squared theta is sitting there, so we know there's a spin 2. So let's write that piece out. So let me forget the 9/4. Cos squared theta minus 1 over 9 is, well, cos squared theta minus 1 over d, which is the spin 2 Gegenbauer polynomial, plus 1 over d minus 1 over 9. And so from here I see that indeed I have a spin 2 particle. I also have a spin 0 particle. But if the number of spatial dimensions is bigger than 9, there's a ghost. And the theory is not unitary. So that's how I discover that string theory has to live in 10 dimensions or less. Okay. You see, it's not trivial. Not at all trivial that this 2 to 2 amplitude is unitary. You can't just crap out a function. You have to check. And it's not even true. You go to more than 10 space-time dimensions, and the theory is not unitary. Okay? Now, I invite you to try to prove that if you stick in d equals 9 spatial dimensions and go to higher and higher points, that the answer is always unitary. Proving it directly is surprisingly hard. I've failed to do it for many years. I would love to know how to do it. So let me summarize. So that shows that these rules work. They have teeth. But in the end, the rules tell us the following thing. That there's a representation for the amplitude when t is fixed that has the following structure. We know that it can't grow even as fast as s squared. So there are some pieces that I can't control. So there's some a of t plus b of ts. In the old days, these would be called subtraction terms. Okay? But after I take those out, in other words, since I know the amplitude goes like, if I divide by s cubed, everything is fine. So there are these pieces that I can't tell you anything about. But after them, everything else has to look like a sum over a spectrum, some spectrum that I don't know. The sum might be an integral, right? A sum over a spectrum and some spectrum of spins, p and s, Gegenbauer polynomials of 1 plus 2t over m squared over s minus mn squared. And there are two things here that are positive. The spectrum is positive, and these probabilities are positive. Okay? So this is an interesting representation of any 2 to 2 scattering amplitude. Again, it's in this limit where t is fixed. It's not necessarily 0. But beginning with this, and now I don't have time to tell you anything about it, but beginning with this, you can go back to the general problem. You see, now I can take this formula and just Taylor expand in t and s. Okay? I can Taylor expand this in t and s and get an expression for all the higher corrections for the powers of s to the p and t to the q that you can get in a low energy expansion. Okay, so it has a concrete expression for every one of those coefficients in terms of what you get from Taylor expanding the propagator and what you get from Taylor expanding the Gegenbauer polynomials. We have already seen one application of this, which is when we just set t to 0 and we just Taylor expand the propagator and we just keep the first term. Okay, sorry, there's also the U channel, I forgot. So we can have the U channel here as well with exactly the same formula, just with s replaced by u. Okay, and we could conclude from that that the sign of the s squared term is positive, but in fact you can make an infinite number of other statements, and those other statements follow from more hidden positivity facts about this propagator and about the Gegenbauer polynomials that I won't have time to talk about, but at least we've set up the problem. Now it's a mathematical problem. Okay, now it's a mathematical problem, and you just have to investigate the properties of this Taylor expansion, which looks rather trivial, but actually has some beautiful hidden nonlinear positivities associated with it, and also the Gegenbauer polynomials that similarly have, both of these problems end up being associated with matrices that have all positive minors. Okay, so there's some this interesting phenomenon of total positivity for matrices.